A distributed parameter system is a system whose state space is infinite-dimensional. Such systems are therefore also known as infinite-dimensional systems. Typical examples are systems described by partial differential equations or by delay differential equations, linear time invariant distributed parameter systems, abstract evolution equations, discrete time with U, X and Y Hilbert spaces, and L and L. The following equations determine a discrete time linear time invariant system, with a sequence with values in X, a sequence with values in U and a sequence with values in Y. Continuous time. The continuous time case is similar to the discrete time case, but now one considers differential equations instead of difference equations. An added complication now, however, is that to include interesting physical examples such as partial differential equations and delay differential equations into this abstract framework, one is forced to consider unbounded operators. Usually A is assumed to generate a strongly continuous semigroup on the state space X. Assuming B, C and D to be bounded operators then already allows for the inclusion of many interesting physical examples. But the inclusion of many other interesting physical examples forces unboundedness of B and C as well. Example: a partial differential equation. The partial differential equation with an given by fits into the abstract evolution equation framework described above as follows. The input space U and the output space Y are both chosen to be the set of complex numbers. The state space X is chosen to be L2. The operator A is defined as it can be shown that A generates a strongly continuous semigroup on X. The bounded operators B, C and D are defined as example. A delay differential equation. The delay differential equation fits into the abstract evolution equation framework described above as follows. The input space U and the output space Y are both chosen to be the set of complex numbers. The state space X is chosen to be the product of the complex numbers with L2. The operator A is defined as it can be shown that A generates a strongly continuous semigroup on X. The bounded operators B, C and D are defined as transfer functions. As in the finite-dimensional case, the transfer function is defined through the Laplace transform or Z transform, whereas in the finite-dimensional case the transfer function is a proper rational function. The infinite dimensionality of the state space leads to irrational functions. Discrete time. In discrete time, the transfer function is given in terms of the state space parameters by and it is holomorphic in a disk-centered it. The origin. In case 1, Z belongs to the resultant set of A. The transfer function equals. An interesting fact is that any function that is holomorphic in 0 is the transfer function of some discrete time system. Continuous time. If A generates a strongly continuous semigroup and B, C and D are bounded operators, then the transfer function is given in terms of the state space parameters by for S with real part larger than the exponential growth bound of the semigroup generated by A. In more general situations, this formula as it stands may not even make sense, but an appropriate generalization of this formula still holds. To obtain an easy expression for the transfer function, it is often better to take the Laplace transform in the given differential equation than to use the state space formulas as illustrated below on the examples given above. Transfer function for the partial differential equation example, setting the initial condition equal to 0 and denoting Laplace transforms with respect to t by capital letters, we obtain from the partial differential equation given above. This is an inhomogeneous linear differential equation, with as the variable s as a parameter and initial condition 0. The solution is substituting this in the equation for y and integrating gives so that the transfer function is transfer function for the delay differential equation example preceding. Similarly as for the partial differential equation example, the transfer function for the delay equation example is Controllability. In the infinite-dimensional case, there are several non-equivalent definitions of controllability which for the finite-dimensional case collapse to the one usual notion of controllability. The three most important controllability concepts are exact controllability, approximate controllability, null controllability. Controllability and discrete time. An important role is played by the maps which map the set of all u-valued sequences into X and are given by. The interpretation is that is the state that is reached by applying the input sequence u when the initial condition is 0. The system is called exactly controllable in time n if the range of equals X. Approximately controllable in time n if the range of is dense in X. Null controllable in time n if the range of includes the range of n. Controllability and continuous time. In controllability of continuous time systems, the map given by plays the role that plays in discrete time. However, the space of control functions on which this operator acts now influences the definition. The usual choice is L2, the space of u-valued square integrable functions on the interval, but other choices such as L1 are possible. The different controllability notions can be defined once the domain of is chosen. The system is called exactly controllable in time t if the range of equals X. Approximately controllable in time t if the range of is dense in X. Null controllable in time t if the range of includes the range of. Observability. As in the finite-dimensional case, observability is the dual notion of controllability. In the infinite-dimensional case, there are several different notions of observability which in the finite-dimensional case coincide. The three most important ones are exact observability, approximate observability, final state observability. Observability in discrete time. An important role is played by the maps which map X into the space of all y-valued sequences and are given by if k n, and 0 if k greater than n. The interpretation is that is the truncated output with initial condition X and control 0. The system is called exactly observable in time n if there exists a NOS greater than 0 such that for all x. Approximately observable in time n if is injective. Final state observable in time n if there exists a NOS greater than 0 such that for all x. Observability and continuous time. In observability of continuous time systems, the map given by for s 0 t and 0 for s greater than t plays the role that plays in discrete time. However, the space of functions to which this operator maps now influences the definition. The usual choice is L2, the space of y-valued square integrable functions on the interval, but other choices such as L1 are possible. The different observability notions can be defined once the codomain of is chosen. The system is called exactly observable in time t if there exists a kt greater than 0 such that for all x. Approximately observable in time t if is injective. Final state observable in time t if there exists a kt greater than 0 such that for all x. Duality between controllability and observability. As in the finite-dimensional case, controllability and observability are dual concepts. The correspondence under duality of the different concepts is exact controllability, exact observability, approximate controllability, approximate observability, null controllability, final state observability.